In this chapter, we'll be looking at hashing consideration for search optimization. Hashing plays an important role in searching key in a hash map or a hash set. Here are some points to consider for optimizing the performance. The fields used in hashing must be a subset of fields in equality. If this is not there, the distinct keys might return same hash code. The elements will get stored in same bucket, and hence the search might not be optimized. Similarly, we need to ensure that hashcode algo is returning distinct values. If this is not the case, different keys might return same hashcode and they'll end up in the same bucket, which will result in deterioration in the search. Also, we can consider caching the hashcode. We'll be looking at demo examples for each of these. Before we look at the demo examples, we need to understand how the search works. Here is the internal representation of a hash set. So hash set maintains an array of specified capacity. By default, the number of elements in that array will be 16. Each element in the array is called a bucket. These buckets are indexed by 0, 1, 2, 3. Each bucket contains a reference to singly linked list. The elements are stored in the linked list. The HashMap structure is similar, just that each element will be storing a pair, which is a key and a value. Let's look at how the search in a hash set works. There are 3 steps. In the first step, it will compute the hash code for the search key. Second, it will try to find the index of the bucket using hash code ampersand n-1, where n is the capacity. Once we get the index, it will get the linked list corresponding to that bucket, and then it will iterate to each of the elements in the linked list, and the first matching element in that linked list will be returned. It will use the equals implementation to compare the objects. Let's look at a simple search example. Here we have a string fig and we are trying to search fruit set. So we are using fruit set.contains s1. First, it is going to compute the hash code for fig. In this case, it is 101.411. Then it will compute the index. It needs to know which bucket might have this. So in this case, it will compute index equals to 101.411 and 8 minus 1. So 8 is the capacity. So we'll get 3. So then it has got a reference to the linked list, which possibly might have the element it is trying to search. Then it will iterate through the list and it will return the first matching element. The matching element is where the equality operator will return true. In this case, it will be the second element. We'll be demoing 3 examples. In the first case, we'll have a bad hashing algo and we'll see how it impacts the performance. In the second, we'll try to fix the bad hashing so that it returns hash code, which are fairly distributed. In the third case, we'll try to cache the hashing code in order to further optimize the search. This is a demo about bad hashing algo. So our basic construct is fruit2, which contains the name of the fruit that we need to store. It is having a constructor which is taking the name of the fruit and we are assigning it to the data member. Then we have a hash code implementation. So this hash code, you can see that we are using math.random *10. So it is going to return value from 0 to 9. And then we are doing a %2, so it is either going to return 0 or 1. So which means any fruit we are trying to store is either going to be stored in bucket 0 or bucket 1. Now let's take a look at how we are going to use this. So we have this class fruit bad hash code demo. We are having a fruit set, which is a hash set. We are having add elements. So these are the number of fruits that we need to add. So we are iterating from 0 to element count. And we are creating a dummy fruit. So you can see we are using sync.format, creating an object of fruit2, and we are trying to store it in HashSet. Then we have search elements. The objective of search is just to search the fruit in the fruit set. We are using Java 8 feature streams, and we are iterating through the fruit set. And for each fruit, we are doing a search against the same fruit set. The return value is going to be true or false, but we are ignoring it since we don't really care about it. We are just trying to search the fruit in the fruit set. Clear is a helper method to clear the fruit set. Then we have a public static method, verify. In here, we are creating an object of this class. We are having a result list which is containing formatted string of the search performance. You can see we have element count of 10,000, which means we are attempting to create 10,000 fruits. We are using util.get execution time. You can take a look at the implementation of this. Here we are passing object and the method name to be invoked and argument to that particular method. So once we execute that particular method, it is going to return us the amount of time it to execute this particular method. So that duration, then we are formatting into a string and basically storing it in the results list. We are doing the same thing for the search elements method as well. And eventually we are just going through the result list and trying to log it. Now with this said, let's try to run this. So let's try to run it one more time. For adding 10,000 elements, we are taking almost 1.2 seconds. And for searching, we are taking 1.8 seconds. Naturally, this is not optimal because the way our hash code is designed is it is going to always fall into one of the two buckets, 0 or 1. So let's try to optimize this in our next demo example. In this demo example, we'll be fixing previous bad hashing. We have created fruit3 class. Instead of having the hash code which was earlier returning 0 or 1, we are having a proper implementation of hash code. This is the default implementation which Eclipse provides once you auto-generate this code. The other methods remain same. We are having this class fruit good hash code demo. We are creating a fruit set and then we are having a same add elements. We are adding this many number of fruits. Then we have search. We are just again using Java 8 feature streams and iterating through the fruit set. And we are doing a search. We are not caring really about the result because the objective here is just to search and see how much time it takes. We are having a clear and then we are having a static method verify where we are creating an object of this. We are using a results list to store search result performance. And you can see we are first calling add elements through reflection. So util.get execution time is going to invoke the specified method on this particular object. And it is going to return as duration. That duration is in nanoseconds. We are using util.nano to ms to convert into milliseconds. Similarly, we are calling search results and then we are trying to log us. Now, if we try to run this, we'll see what the result is. So for 10,000 element, add elements is taking 113 milliseconds and search is taking 112. We'll try to run it again. If we compare this to our previous result, you can see that earlier for 10,000 elements, this was taking 1.2 seconds. Now it is almost 0.1 second. And in case of search elements, earlier it was taking 1.8 seconds and now it is 0.09 seconds. So it's a huge improvement. In the bad hashing demo, the elements will get added to the linked list either in bucket 0 or bucket 1. It has to perform linear scan in the linked list to find the matching element. Hence, the performance is poor. In the good hashing demo, the hash code is correctly computed. Hence, the elements get distributed fairly well, possibly resulting in one element in each linked list, unless there are of course collisions. Hence, the search is optimal here. Ensuring that hash code is correctly computing the hash code is very essential so that your search is highly optimized. Next, we'll look at caching of the hash code and see the impact on the performance. In the third example, we have fruit4. It is having same internal implementation except that the hash code we have modified it such that we are trying to cache this in hashcode underscore. Hashcode underscore we have declared to be of type int. Every time when the hash code is not already computed, we are trying to compute it and then storing it in a hashcode underscore. And if it is already computed, we are just returning it so that we don't have to recompute it. That's the only difference. All other codes remain same. You can see we are having add elements, we are having search element, we are having clear, and we are having verify, which is trying to create 10,000 elements, and it is invoking add elements, and then it is also invoking the search element. And then we are trying to just print this. Now let's try to run this. So if we compare this result with our previous one, we can see that there is a little bit improvement. So earlier it was 96 milliseconds for 10,000 elements, but now we are getting around 88 milliseconds. The improvement will be much more if your key is much more complex. Right now it is just having one string. If we have multiple data elements which are used as keys, then trying to compute a hash code using all those data elements which are part of the key will have even higher impact on the performance. Caching demo has the best search performance since it doesn't have to recompute the hash code. So that concludes our optimization with respect to hash code.